Okay, so in this video, we're going to take a look at Rubinstein and Jarrow and consider convergence to the Black-Scholes model. And we'll visualize this in using Python code, and we'll execute in the Google Colab. Starting point here perhaps is to just take a look at where initially I took the code from. It was from a GitHub. I've made a few small changes, but basically the code is intact. Click on the link. That'll bring us to Yuchen Amber Lu, and we'll look here in her Jupyter notebook and the binomial, so the snippet of code related to the binomial model. And if we open that up, we'll see there's two different trees presented here. There's Cox, Ross, Rubinstein, and then we have Jarrow, and there's more here, but we'll try to replicate to some degree these graphs, but we'll change a little bit the tenor of the step size, and we'll look at different oscillation type behavior for different step size. So broadly speaking, we'll follow the code here in this GitHub, and we'll alter a little bit the step size. So let's copy our snippet of code. So we'll just copy, and we will then go into Google Drive, right? And we just basically go new, and then we look for the Google Colab. And if I just click on that, the online browser, the compiler here will open up, and I can paste. So to paste, just Control V, just as simple as that. And okay, so that's the code gone in. We could do a little bit of editing, maybe by removing the additional lines that have been put in, but nothing strikes me here as being too much out of place. Just to note, if you're in the Google Drive, you come here to New and then More, and you don't find the Google Colab available, just come down to Connect More Apps, and then just look for the Colab. And you see it comes up, and if it's not installed, just come down here and click on this icon. It takes about 2 seconds, maybe 10 seconds for it to load up. It generally installs very quickly, right? So, okay, we already have it there. We already have our Python code loaded in. Let's execute that. Okay, so we let me see. Let's just execute this code. So this code, let's just execute, and it takes a second. We have to be careful on some elements of the code versions that I had. There was a gap between 3 and parentheses. Also make sure we have a colon included here at the end of this parenthesis. Likewise with Jarrow 3, make sure we remove the gap and include colon here. And then the output that we get in terms of the tree is Cox, Ross, Rubinstein, and Jarrow going from 0 to 1,000 steps in intervals of 5. So if we go back to, this is the call option. If we take these parameters, values of S100, K being equal to 100, T1 year R equal to 5%, sigma equal to 0.2. Now we didn't include a different yield in the tree, but we did include that in the Black-Scholes model. We could have left it out, but it's there. And when we take these parameters, we know that the European option, if we were to value the European call option, the value of the call would be 1045,058. When we look at Jarrow Rudd and Cox-Ross Rubinstein convergence to 1045, you can see at the low step size, there's quite a bit of oscillation. As we increase the step size, we get closer and closer to true for both binomial frameworks. We might notice that if we look here for a moment with the Cox-Ross-Rubinstein tree, we started at step 10, we went up to 1,000 steps and in intervals of 5, so 10, 15, 20, 25, all the way to 1,000, and that produces this type of oscillation. If we just went up to 100 steps, in steps of 5, we're again going at odd numbers and even numbers. So if we go from 10, 15, 20, 25, you can see that we oscillate. And the blue here is denotes Cox-Ross-Rubinstein, and the orangey brown is Jarrow Rudd. Again, this is for the put option using Black-Scholes model. Printing out the put, we get a value of 557.35, and you can see here that going up to step 100, we're converging. There is oscillation, but I can kind of make out we're getting closer to that 557.